Man, that one. Yeah. These two pages I'm giving you.
Hey guys, how was the competition?
You're worried about the wrong factors of safety.
Okay.
Yeah.
Was that- was that-
More worried about the safety of it actually.
Good to see you. How's your spring break?
It was amazing.
Watch competition went well?
Good. Did you see the video at all?
No. I heard from Jessica. She kind of told me what happened, but she said that you'd show me the video.
I'll show you the first video. And then I'll show you the actual video.
All right. Wait, what does that mean?
Okay, so this is the first one.
Okay.
It was pretty important.
Oh no. Oh.
Yeah. Because it was a 30, almost 30 wind miles per hour. Wind gust. It was bad. We got kind of screwed there, but here's the second one, the successful flight.
All right. There we go. Nice. There we go.
This bank right here is pretty cool. It's my favorite part.
Nice. Ooh, that's awesome. Dang, that must feel so good.
It was amazing.
Nice. That's great. That's awesome. Now the landing.
That was what went wrong.
Okay.
So our pilot, he was telling us that our aileron response was a little bit dampened there.
Oh,
So
I see. I see. That's great though.
Yeah,
That's awesome. Congrats, guys.
thank you. But yeah, my bad. I know I've been lacking in your class.
No worries. No worries.
But I'm locked in now.
All right, sounds good.
I'm not gonna sleep with the class anymore.
Okay,
I apologize for that.
Sounds good. I didn't even notice.
Well, just so you know how it's not happening.
That's why I told you when they met being worried about the wrong factors.
Okay, I see. I see. All right, it's 1 o'clock. Let's go and get started. All right, welcome back, everybody. How was everyone's spring break? Good, good. Good to see everybody. Now we're back for the final sprint towards the finish line. So we have about 5 more weeks, and then we'll be off for summer. So, but of course, you know, our time here is going to be quite busy. So first thing we have is a midterm exam. That's probably the first thing on everyone's mind. So our next midterm is going to be next Thursday, April 17th. So format of the exam is going to be same as the first exam. So it's going to be 50 points. You can bring a cheat sheet, calculator, writing utensil. and it'll be taken in class, okay? One thing about this exam compared to the first exam, it's there's going to be one less question. So if you probably have noticed from the homework problems that these convection problems are quite long. So I can't ask you 3 problems on this exam and you know and have you guys finish in a good amount of time. So there's only gonna be 2 problems to solve. They are longer, and so that I think the overall length of the exam is probably going to be the same, maybe a little bit longer than the last one. So just kind of be prepared for that. Okay. Yes.
But within those 2 questions, it's like a whole bunch of different questions.
Yes. Yeah. So each question probably you can expect maybe 3 or 4 or 5 parts to it.
Okay,
Yeah.
thank you.
Yeah, but just like the first exam, you know, you can expect the exam questions to be quite similar to the homeworks that you've been doing. So homework 4, homework 5. And I do have one last kind of very short homework assignment, homework 6 for you guys for next week. Yeah.
Are we gonna have to like look up stuff on a table or you give
No.
us stuff like?
Yeah, so for the fluid properties, I'm just gonna give it to you straight in the problem. You know, looking things up in a table, I think it just adds time just for no good reason. So it helps my grading too for everyone to have consistent values. So I'll give you the values in the exam. You just have to plug them in into the right formulas. Yep. One other thing I'm going to provide for you guys, not explicitly for the exam, but you know, probably you guys have noticed that there's been a lot of formulas that we've been going over. So I did make a handout for you guys to kind of summarize everything from the convection unit. So that is it's actually already up on Canvas. It's been up since the beginning of the semester, but I haven't put it in a convenient spot.
So for that, is that kind of all the information we'll need for the exam? Or do I-
Yes, yeah. I mean, the handout is much longer, so it's too long to bring for the exam. And so it's gonna be up to you to kind of pick and choose different parts of that to put on your cheat sheet. Yeah, so the handout itself, I think, is like 5 or 6 pages. That's how much we've been covering in the past few weeks.
I'm assuming the handout is just gonna have like the correlated Russo.
Exactly. Yeah. So it's going to give you all the different situations for the NUSO correlations and then tell you kind of what the formula is and what the setting to use that in. Yep. Okay. So plan for today is we're going to be going over our last chapter in our convection unit, which is heat exchangers. So for this one, you know, I do want to finish this by the end of this week. And so I don't think we'll have time to do everything for heat exchangers. But I do want to get to kind of the most important parts because heat exchangers are actually pretty important if you work on any kind of thermal system after graduating. So it's important to know at least some of the basics just so that you can kind of go in and know what the heat exchanger does. Okay. All right. So that's the plan for today and for Thursday. All right. Any questions before we begin today? Okay. All right. So let's go ahead and get started. Okay, so topic for today is heat exchangers. And so we'll be talking about heat exchangers a lot for this week, and so you'll see me use this acronym, which is just HEX. And so when you see HEX just stands for heat exchangers. Okay. Okay. So heat exchangers is kind of a very interesting kind of chapter to go over because, you know, so far everything that we've been covered has been very, I would say, kind of very theoretical, very conceptual. Heat exchangers is kind of a very much an applied kind of subject, okay? And so you can think of this as kind of like an application of mostly internal convection. So I saved this one for the end because, you know, I wanted to get all the theory stuff out of the way and then, you know, and then we'll talk about the application kind of at the very end, right? So there's not really any new theory that we're going over today. There are new formulas, but really everything that we're going over is just an application of what we've already discussed in internal convection, okay? All right, so what is a heat exchanger? So a heat exchanger is a specific type of engineering device that's designed to exchange heat, just like the name, between 2 fluids. Okay. So there's lots of different designs for heat exchangers. And so, we're not going to go over all the different types of designs. But for our purposes, we're going to stick to kind of a fairly simple design where you have kind of two fluids just kind of flowing right next to each other. So it looks something like this. Okay, so in each of these channels here, we have two fluids. And so we'll have fluid 1 and fluid 2. Okay. Usually one of these fluids is going to be hotter than the other one. And so, in order for there to be heat transfer, there has to be a hot fluid and a cool fluid. Okay. Right. And so maybe fluid 1 is flowing this way. Maybe fluid 2 is going the other way. Okay. And then we have heat. So let's say fluid 2 is hotter than fluid 1. And so you're going to have an exchange of heat that goes like this. Okay. Okay. So this is a very, very common situation you're going to see in a lot of applications for thermal engineering. So, some examples of this would be, any kind of air conditioning system or refrigeration system. Your refrigerator has a bunch of heat exchangers. Your car has a bunch of heat exchangers going on. Radiators, power plants, chemical plants. There's almost always a situation where you want to exchange heat between two fluids that are going to be flowing past each other. Okay. Okay. All right, so let's talk about different types. Okay. And so the exact geometry and the exact arrangement of the heat exchanger really kind of depends on its application. Okay. Let me kind of draw a couple for you here. Okay. Right. And so, the way I drew it here, it kind of looks like you have two liquids that are flowing past each other, but you can also have a liquid and a gas as well. Right. And so one common type of heat exchangers is a cross flow heat exchanger. Okay. So a cross flow heat exchanger kind of combines kind of this idea of convection together with fins. If you kind of remember, we talked about that a long time ago, right? So in a cross flow heat exchanger, one example might be, maybe you have these kind of slats to kind of direct airflow. Okay. So you have these kind of parallel slats that are kind of going like this. And airflow is going in between the slats. Right. And then through the slats, you might have these pipes that carry a fluid. Okay. So you might have pipes of fluid that kind of go through the different slats. I know this is a terrible drawing, right? Right, but inside these pipes might carry some kind of hot fluid. Right? So maybe not, a heat exchanger in kind of the traditional way. This is an exchange of heat between, the hot fluid inside the pipes and the cool air that's going by, right? So this would classify as a heat exchanger. Okay. Another common one, the one that we're going to focus on mostly in this class, is called a concentric tube heat exchanger. And so in a concentric tube heat exchanger, you basically just have one tube inside another tube, okay? And so you may have just a regular pipe that looks like this, okay? And then that's going inside another pipe that's kind of bigger than it, like this. Okay. Okay, so I've kind of exaggerated the inner pipe here just so you can kind of see. But inside the inner pipe, you might have fluid 1. Okay. And in the gap between the inner pipe and the outer pipe, you might have fluid 2 that flows in from here. Okay. Okay. All right, and so if you actually take a cross section, and so it would look something like this. And so we have kind of it looks like 3 pipes here, right? where this inner pipe here, that's kind of the innermost pipe. And then kind of the two ones surrounding it, that's the other fluid. So inside here, you might have fluid 1. And then surrounding it, you have fluid 2. Okay. Fluid 1 might be flowing this way, and we'll say fluid 2 is flowing in the same direction. Okay. Okay, and there's lots of other designs, for heat exchangers and lots of different applications, but conceptually in terms of its heat transfer, they all kind of work under the same principles. It's just that the flow patterns are going to be a little bit different. Okay, so for this class, for this week, since we don't have that much time, we're going to focus mostly on just the concentric tube heat exchanger. Just because it kind of has the simplest flow out of every heat exchanger design that we have. Okay, because what do we have here? So for the inner pipe, we've already kind of discussed this a lot. So for the inner pipe here, we just have simply flow in a cylindrical pipe. Okay. So we already know how to compute that. We know how to compute Nusselt numbers in those situations. We know how to compute heat transfer, right? We've been dealing with that kind of this whole class, right? And then around it, we have, a different kind of flow, but, one that's actually not too different than what we've seen. So in the outer pipe here, we have what's called flow in an annulus. Okay. Question, yes.
See how you denoted that the direction of the two fluids are going in the same direction?
Mhm.
Is that always the case?
That's not always the case. And so actually, whether they're flowing in the same direction or opposite directions, it's going to change the performance of the heat exchanger. So we're going to talk about that.
Yeah, because I mean, I don't know if I'm jumping the boat, but wouldn't it be more convenient for the other fluid to go in a different direction?
It depends. It depends on kind of the constraints you have in the problem. So when they're going the same direction like this, that's called a parallel flow heat exchanger. So that's going to have certain properties. And then if they're going in the opposite direction, that's called counterflow. And that's going to have other properties as well. So there's pros and cons to either.
Oh,
Yeah.
thank you.
Yep. Okay, so for concentric tube heat exchangers, we have flow in a pipe, which we know, and then flow in an annulus, which we haven't done yet, but it actually is very similar to flow in a pipe. Okay, so as we develop the theory, as we develop the equations for heat exchangers, we're going to focus mostly on this concentric tube heat exchanger. And then a lot of what we discuss will apply to other types as well. Okay, but just know that there's a lot of other types of heat exchangers out there. So and some of you may have already been working with heat exchangers already, let's say if you're part of one of the teams, or maybe part of your senior design project as well. So probably most likely the heat exchanger you've been working with looks different than this, but I did want to highlight that a lot of the theory that we are going to discuss does apply to other heat exchangers as well. It's just kind of convenient to focus on this one, just because the fluid mechanics is relatively simple for this type of heat exchanger. Okay. Any questions on this so far? Okay. All right. So let's talk about the thermal aspects. Okay. So let's talk about heat transfer in a heat exchanger, or how can we start to quantify this? Okay. Okay. So first of all, let's state one of our assumptions, and so we're going to assume that all of the heat exchangers that we're going to be considering is in a fully insulated system. And so what that means is that any heat that gets exchanged is only going to be between the two fluids. And so we're going to assume that there's no heat loss to the environment. Okay. that may not be necessarily true in reality, right? So we've talked before, it's almost impossible to get a true, fully insulated situation. But it just makes our computation more convenient. Yeah.
I know this is just an assumption, but does that mean like a car radiator is not technically a heat exchanger? It's only releasing heat to the environment.
The environment in that case would be the other fluid. So it'd be something like this crossflow heat exchanger where one of the fluids is coming from the environment. So it's exchanging fluid, heat to that other fluid. Yeah. Mm-hmm. Yeah. But with this assumption, the only heat that we're going to be considering is going to be heat transfer between the two fluids. Okay. Okay. So visually, it might look something like this. So if we look at our concentric tube heat exchanger, okay, and basically we're going to be assuming that outside the outer pipe, we're going to have kind of an insulated surface. We have kind of very good pipe insulation on the outside. Okay. Right. So the only heat that gets exchanged is going to be, between the two fluids. Okay. Okay. That's important because, it's going to kind of form the basis of our equations. Okay. One other thing that we need to make note about this type of device is that because, for the most part, for our concentric tube heat exchanger, we're looking at two internal flows. We're not considering any flow from the environment. Both fluids are going to be considered internal flows. Okay. So let me kind of mark on this figure again. So on the inner pipe, we'll have fluid 1, outer pipe will have fluid 2 kind of flowing around it. Okay. So both of those are internal, we consider kind of internal flows. And so that has a lot of consequences, but the most important consequence is that the temperature of both fluids is going to change along the length of the heat exchanger. Okay. In fact, there's a notion, or there's a way that we kind of describe these heat exchangers in terms of the inlet temperature of the fluid and the outlet temperature of the fluid. Okay. So let me come back to this drawing here. Let me erase these kind of red arrows here. Okay. Now let's assume that we have a parallel flow arrangement. So let's say that, both fluids are going from left to right in this case. So the fluid 1 is going from left to right, fluid 2 also going from left to right. Okay. And so if the direction of our flows is like this, then we know that one side of our heat exchanger we consider the inlet. That's where the fluid's coming in from. And the other side of the heat exchanger is going to be our outlet. That's where the heat goes out from. Okay. So for fluid 1, right, what we can quantify here is we can quantify the temperature, mean temperature of fluid 1 at its inlet. Okay. Actually, let me do it this way. We don't need TM. We'll say T1 inlet. Okay. And we also have temperature of fluid 1 at the outlet. So T1O. Okay. So T1I, T1O. That's just the mean temperature of the fluid at the inlet of the heat exchanger and the outlet of the heat exchanger for fluid 1. Okay. And we can do the same thing for fluid 2 as well. So for fluid 2, we have the temperature of fluid 2 at the inlet and temperature of fluid 2 at the outlet, okay? And since this is concentric tube, that same temperature is going to apply, in this cross section, it looks like there's a top and bottom portion, but it all kind of wraps around this fluid. Okay? So you have T2 inlet, T2 outlet. Okay. So a lot of how we're going to describe these heat exchangers is based on its inlet and outlet temperatures for the two fluids. Okay. Okay. And so if you know that information, so if you know kind of the inlet temperature and the outlet temperature of even just one of the fluids, you can use that to actually compute the total amount of heat transfer that gets moved inside the heat exchanger. Okay. So knowledge of the inlet temperature, knowledge of the outlet temperature gives you a heat transfer. Yes.
I'm sure you'll get into this, but how does that inner tube affect the like the cross-sectional shape of the mean temperature? Like the outer pipe versus the
Yeah, no, that's a really good question actually. So it depends on whether the inner tube is hotter than the outer fluid temperature. And so probably what you're going to see is that it's going to be a quadratic function. So it's going to have a quadratic shape, but it's going to vary from one end to the other end. So something like this. I said that and I visualized in my head, but then I realized it didn't come out on the paper. Okay, so for the outer tube, right? Right, so this is the outer tube out here. Okay, so let's say in this case the outer tube is cooler, or the outer fluid is cooler than the than the inner, right? And so we can plot out the temperature distribution like this, where let's say that we start at a temperature here, and maybe it kind of decays down just like that. Yeah.
So just have that sort of
Exactly. Yeah. Yeah. And then you have the same thing down here too. So it starts at the higher temperature here and decays down just like that.
That's
Yeah.
assuming flow to the right.
I think for the temperature distribution, it doesn't matter. The only thing that matters is just the temperature difference. Yeah.
And then the
Inner.
so influenced by the outer.
Yeah. So the inner temperature, if the inner fluid's hotter, it might look something like this. Like that. Yeah. So they meet at the same temperature at the interface, and then they grow up or grow down depending on the mean temperature of the fluid. Yeah. Okay. All right. So if you know the inlet temperature, you know the outlet temperature, you can compute the heat transfer. Okay. So this is a formula I kind of, I don't remember if we covered it with internal convection just because I was kind of saving it for heat exchangers. But what you can do is you can say the Q convection for an internal flow is equal to the difference of the inlet temperature minus the outlet temperature. Okay. This is inlet temp, outlet temperature. Okay. Sure. Yep. Okay, so Ti minus To, of course, it depends on which one's hotter. And so, you're going to swap these if the fluid's heating up. But this equation here assumes that the fluid is cooling down. So inlet temperature higher than outlet temperature. Okay, multiplied by m dot, which is the mass flow rate of the fluid going through the pipe, multiplied by Cp, which is the thermal capacity of the fluid. Okay. So m dot is mass flow rate, Cp thermal capacity. So mass flow rate is nothing more than just, the amount of mass that's passing through the fluid at a given time. So usually you're gonna obtain that from the volumetric flow rate or the mean velocity multiplied by the density. Okay. And CP is a property of the fluid. So that's a property that you're going to look up in one of your tables. Okay. CP has been there throughout this entire unit. It's just that we haven't really used it for anything up until this point. So CP is a material property of the fluid. Okay. So this formula here, I would say is probably the most important formula. We're going to go over a lot of other ones in heat exchangers in this entire unit, but this is probably the most important one that you're going to need for this chapter. Okay. Okay, so this is just heat exchange to an internal fluid, right? So we know that for internal flow, the mean temperature is going to be changing, so you can actually quantify the amount of heat that gets exchanged.
What if you have two different fluids? Would the thermal capacity of the fluid be the inner? Would it be the outer?
So you can make an equation like this, one for the inner fluid and one for the outer fluid as well. And actually, that's kind of the first example that I want to kind of go over with you guys. Okay.
I think you kind of just had this.
Well, you kind of set up two equations, but you just say that their Q is equal to each other. You'll see in a second. So one very common situation is, let's say that you have a heat exchanger and you know the temperatures for, well, you know the inlet and outlet temperature for one of the fluids, but you want to find out the outlet temperature for the other fluid. Okay. Okay. So let's say that we want to find outlet temperature for fluid 2. Okay. Okay, so let's draw our heat exchanger. For now, we're going to assume a parallel flow, but that formula up there is valid for counterflow as well. Okay, so we have fluid 1, fluid 2, fluid 2. Okay. So for fluid 1, let's assume that we know both the inlet and outlet temperatures of fluid 1. So we know T1 I and T1 O. Okay. And for fluid 2, let's say that we only know the inlet temperatures. We know T2 I, but T2 O is unknown. Okay. So we know, so let's see our knowns here. So you have T1 I, T1 O, and T2 I. Okay. And of course, we know the properties of the fluids, so we know CP 1, CP 2, and the mass flow rates are known as well. So M1 dot and M2 dot. Okay. Okay, so based on all this information, let's compute the outlet temperature of fluid 2. Okay. So very quick example. This one's actually not in the notes, but I think it's important to kind of go through. So in this situation, we have kind of everything that we know, right? Because remember the one assumption that we make with these heat exchangers is that we have no loss of heat to the environment, right? So around the outer pipe here, around fluid 2, we have kind of perfect insulation. So all the heat that gets lost from fluid 1 will be gained by fluid 2, or vice versa if fluid 2 is hotter than fluid 1. So, keep in mind here that we haven't made any assumptions based on which fluid is hot or cold. Okay. Okay. So the way to approach this problem is that, we can compute the heat transfer from fluid 1 based on everything that we know from this problem. So Q for fluid one is equal to M1 dot CP1 multiplied by T1 I minus T1 O. Okay. So all this information was given to us in the problem, so we can compute Q from the situation. Okay. And then what we can say is that since this system is insulated, so there's no heat transfer to the outside environment, then this Q is exactly the same Q that's going to be, transferred to fluid 2. Okay. And so what we can say is Q is equal to M2 dot times CP2, okay, multiplied by the difference in temperature between the inlet of fluid 2 and the outlet of fluid 2, okay? Now, just to make sure that the mathematics kind of work out and the signs are correct, one of these fluids has to be hotter than the other one. And kind of what we're assuming by these formulas is that fluid 1 is hotter, because what we're saying is that this difference of T1I minus T1O, right? By assuming that this is kind of a positive number, then we're assuming that fluid 1 is going to cool down. Okay. Okay. Just based purely on on the order of the terms. Okay. And so just to make sure that our number ends up being positive and physically accurate, then we have to swap these for fluid 2. So if we assume that fluid 1 is going to cool, that means fluid 2 is going to heat up. And so that means the outlet temperature of fluid 2 is going to be hotter than the inlet temperature of fluid 2. Okay. So inside this parentheses, we have T2O minus T2I. Okay. So of course, the ordering of these assumes fluid 2 will heat up. Okay. So just kind of be careful of the signs there. So generally, generally speaking, just this is kind of the same as kind of the rest of the class or rest of the semester. Whenever you have a temperature difference, it's always kind of good. It's always good practice to order the temperature difference so that you get a positive number. So higher temperature minus lower temperature. Okay. And since we have a heat exchanger, we know that one fluid's going to start out hot and then cool down. The other fluid is going to start out cool and heat up, right? That means when you are ordering these terms, that means you might do outlet minus inlet or inlet minus outlet. So that's just kind of be aware of that. Okay. Okay. Any questions on this so far? Okay. All right, and so the last thing to do, and so since this is an insulated heat exchanger, we know that these two heat transfers are going to be equivalent to each other. So let's set them equal. Okay. And so by setting them equal to each other, we can solve for the one unknown, which is T2O. Okay, so we set them equal to each other. So we have M1 dot CP1 multiplied by T1 comma I minus T1 comma O is equal to M dot 2 CP2 T2O minus T2I. Okay. And then now it's just kind of algebra to solve for T2O. Okay. So if we do that, I'm just going to do it kind of all in one step here. We get T2O is equal to M1 dot CP1 multiplied by T1 comma I minus T1 comma O divided by M2 dot CP2 plus T2, comma, I. Okay. So this is a very quick example, but just, I did this to kind of illustrate the fact that, within a heat exchanger, any heat that gets lost from one fluid is going to be picked up by the other fluid. And that's going to affect its inlet and outlet temperatures. Okay. And oftentimes, that's kind of what we're interested in the most. So most of the time when you are, designing a heat exchanger or doing computations of a heat exchanger, you're interested in the inlet and outlet temperatures of the fluid. And you're interested in the heat that gets exchanged between the two fluids. Okay, that's primarily what you're going to be, be computing in these kinds of situations. Okay, any questions on this? Okay, good. All right, so let me just leave that note. Most of the time. So first thing is heat exchanged. Q and 2 inlet. Okay. So usually you're going to be solving for one or two of these things in most heat exchanger type problems. Okay. Now there's other things that you can compute. So what we're going to get into on Thursday is we're going to discuss things like effectiveness or efficiency of the heat exchanger. If you think back to our discussion about fins, usually when you design kind of an engineering device, you want to quantify how effective or how efficient it is at doing its job. And so we'll be talking about that, but all of those other quantities are kind of derivatives of these two things. So if you can compute the heat that gets exchanged in a heat exchanger, or you can compute the inlet and outlet temperatures, you kind of have everything that you need to compute most other things. Okay. Okay. All right. So that I think serves as a good introduction to heat exchangers. Let's talk about some more specific types of flow arrangements. Okay. Now, we've already kind of mentioned this, but there are two ways that the flows can be arranged. Question, yes.
Before you move on, I was going to ask real quick about our last example we did last class.
Yeah.
Because we got up to solving RA.
Uh-huh.
And I don't know if we did the other two parts or not, or maybe if I just missed.
Yeah, we didn't. We kind of ran out of time at the end. So, but for this one, once you have the RA, you can compute it. We had our formula for the Nusselt numbers based on these formulas here, and then you compute the convection coefficients from there. Yeah. Mm-hmm. Okay. So let's talk about the different flow arrangements inside these heat exchangers and how that affects, the behavior of the heat exchanger. So the two types that we're going to consider, one is called parallel flow heat exchangers. So we'll talk about that one first. And the other type of heat exchanger is counterflow, which, we'll go over kind of later today. Okay, so in parallel flow heat exchangers, the two fluids move in the same direction as each other. So one goes from, left to right, the other one's going to go left to right as well. Okay. Okay. The name is a little bit misleading because, both in parallel flow and counterflow, you can say that the flow is moving parallel to each other. But when we say parallel flow heat exchangers, it means that the two fluids are in the same direction. Okay. So if we draw our concentric tube heat exchanger, right? We have fluid 1, fluid 2, and fluid 2. Okay. That means both fluids are going in the same direction. So kind of the same as the of the example that we just did. Okay. Okay. So that means that the inlets for both fluids are going to be in the same physical location of the heat exchanger. Okay. So we have an inlet side and an outlet side. Okay. Okay. And so both fluid 1, fluid 2, in this case, the inlets are on the left and the outlets are on the right. Okay. All right. So, before we kind of, look at some graphs and kind of talk about the performance, let's just kind of talk intuitively kind of what we expect to happen in this situation. Okay. So I should say at the inlet, remember, these two fluids are coming in at very different temperatures from each other. So in order for there to be heat transfer, there has to be one fluid that's hot and one fluid that's cold. Okay. So, just for the sake of argument, let's say that fluid 1 is the hot fluid and fluid 2 is the cool fluid. Okay? So that means fluid 1 comes in at a high temperature. And fluid 2 comes in at a low temperature. Okay. All right. And so what happens after that, right? So in the middle of the heat exchanger, so basically after the fluid enters the heat exchanger, the fluids are going to exchange heat with each other, right? And so that means fluid 1 is going to cool down. And fluid 2 will heat up. Okay. Right. And then by the time the fluid leaves these heat exchangers, they're going to be at some temperature that's different from where they started, right? So fluid 1 is going to exit with a temperature that's lower than its inlet temperature, and fluid 2 is going to exit with a temperature that's higher than its inlet temperature. Okay? So at the outlet, and fluid 2 okay. Okay. So all this, may seem obvious, right? But it's good to kind of write these down because once we kind of start to draw graphs and charts and put numbers on this, I think it's easy to kind of lose track of kind of what instinctually or what intuitively should happen. Okay, so let's plot this out. Right. All right. So with that description in mind, right there, let's visualize so we can kind of see what's going on. Okay. So on the horizontal axis here, I'm going to draw that's going to be our physical distance. And so on one hand, we have, I guess if you want to label the horizontal axis, we can call it the length, okay? And so on one end of the horizontal axis, we're going to have the inlet. The other end of the horizontal axis, we're going to have the outlet. Okay. All right, and then on the vertical axis, we'll have temperature. Okay, so let's plot out fluid 1 first. So fluid 1 is our hot fluid. Okay. Okay, so we know that our hot fluid or fluid one is going to come in at a high temperature. And then it's going to decrease to a lower temperature by its out. Okay. Right. So the fluid one is going to follow a trend that's like this. So it's going from T1I and then drop to T1O. Okay. All right. Now let's look at the second fluid. So cool fluid. Right. So for the cool fluid, it's going to come in at T2I, and then as it goes along the heat exchanger, it's going to heat up. Okay? And it's going to heat up to T2O. Okay? Okay. So that kind of just describes or this kind of shows or visualizes kind of what we just described up above. Okay. So a few things to note here. So a few features that we can see. Okay. First thing we notice is that the delta T, or the difference in temperature, right? So if we quantify delta T as just kind of the difference between the difference in temperature between the two fluids at a at a physical location. Okay. The delta T starts out very large in this heat exchanger. Okay. So that's kind of one important property of a parallel flow heat exchanger, is that the temperature difference starts out very, very large, right? Because if you think about it, at the inlet of these fluids, right? The inlet is the hottest that fluid one is going to be, and it's going to be in the location where T2 is the coldest it's ever going to be, right? It's never, T1's never going to be hotter than that, and T2 is never going to be colder than at the inlet. Okay. So the difference in temperature is going to be very, very large there. Okay. And this has a very important consequence, because we know that temperature difference drives the heat transfer, right? And so what this is telling us is that heat transfer, or the amount of heat that gets transferred between the two fluids, is the highest at the inlet of the heat exchanger. Okay. And that's good, because generally, you want, when you design a heat exchanger, you're designing it in a way to maximize the heat transfer between the two fluids. Okay. So it's important to know that the most heat transfer that you're going to get in a parallel heat exchanger is going to be at the inlet or near the inlet. Okay. Okay. But as the graph kind of shows here, as you go along the heat exchanger, this delta T gets smaller and smaller, right? So as we kind of go along, that difference of temperature is going to shrink, because heat is already moving between the two fluids. Okay. And if delta T is shrinking, that means the amount of heat exchange is also going to be shrinking along the parallel flow heat exchanger as well. Okay. So this kind of brings up a really interesting phenomenon that, as you can see that, we can make this heat exchanger longer and longer, but as we make this heat exchanger longer, we start to kind of get diminishing returns in terms of the amount of heat that gets exchanged between the fluids. Okay. So that's one important property of a parallel flow heat exchanger, is that, for a very short period of time near the inlets, you get very efficient heat transfer between the fluids. But as you make the heat exchanger longer and longer, it becomes less and less efficient. Okay. Okay. Another thing that I want to highlight from these two, from this graph right here, right? If we come back up to this graph, we can see that, the two fluids never actually cross paths, right? So in a parallel flow arrangement, it's impossible for fluid 2 to heat up past fluid 1's temperature, right? So there's kind of an imaginary barrier that kind of separates these two, okay? So if we draw kind of a line right in the middle of them, right? It's impossible for the two fluid temperatures to cross that line. So at the most, the two fluids can meet at the line, right? And so we kind of continue this graph right here, right? The two fluids can meet at the middle, okay? But it's going to be impossible for the two to kind of cross that path or cross that line because, once the two fluid temperatures are equal, then it's impossible for any heat transfer to occur because there's going to be no delta T at that point, okay? Okay. So for a parallel flow heat exchanger, there's kind of a hard limit in terms of how much heat that can get exchanged. Question? Yes.
And right now it's being related strictly to length.
Yes.
How we equate it, so we're not gonna be doing it like.
No. So we're assuming steady state in this case. Yeah. So we're assuming everything's kind of steady state. Yeah. Mhm. Okay. So what does this mean? So practically speaking, this kind of gives you, maybe some ideas in terms of what kinds of situations you want to use a parallel flow heat exchanger. So, for a parallel flow heat exchanger, if your space is very limited, and so if you don't have a lot of space to kind of put your heat exchanger in, parallel flow is great because, for short lengths, parallel flow gives you a lot of great performance. Because you have that huge temperature difference at the inlet, that means, for a short period of time, your parallel flow heat exchanger is going to be fantastic, okay? And so if your goal, if the goal in your engineering design is going to be to just cool this fluid down as much as you can in a very short period of time, you can do so in a parallel flow heat exchanger, okay? And if your goal is not to, make the two fluids, change, fully change temperatures, then parallel flow is kind of the best that you can get for that, okay? But, if your goal is to exchange the most heat possible between the two fluids and space is not really a concern, then it's actually better to go with the counterflow. And we're going to go over that in a second. Questions?
Talk about it being insulated, but do the material in between the two pipes would that play a significant role at all, or are we just kind of? Wouldn't that affect the rate of heat transfer?
Oh, yeah, yeah. Yeah, so so the question is, in between these two pipes, there's going to be some kind of solid interface here, right? Just because there's the pipe is going to have some kind of material thickness. And so that does actually make a difference. And so, probably on Thursday, today I just want to talk about counterflow. We're going to be drawing a thermal circuit between the fluid 1 and fluid 2. And so depending on that material that you make that inner pipe out of, that's going to affect the heat transfer between them. Yeah. Mhm. All right, any other questions on parallel flow heat exchangers? Okay, all right, so last thing I want to go over today, let's go over counterflow. Okay, so in counterflow heat exchangers, the two fluids, or one of the fluids is kind of flipped, so that they're going in opposite directions. Okay, Okay, so I'm going to draw our concentric tube heat exchanger one more time here. All right, so we have fluid 1, fluid 2, fluid 2. Okay. So in a counterflow arrangement, these two fluids are going to be in opposite directions. So it doesn't really matter which direction that they are. So let's say that fluid 1 is going to go from left to right, and fluid 2 we're going to assume goes from right to left. Okay, and then let me do this. And so let's label the inlet and outlet for both of these flows. Okay, so for fluid 1, the inlet is going to be on the left, the outlet is going to be on the right. So we have T1I on the left, T1O on the right. And then for fluid 2, it's the opposite. So we have T2I on the right and T2O on the left. Okay. Okay. So what difference does this make? So one fact from before is still going to be true here, that the inlet temperatures of the two fluids are going to be the most extreme the temperatures are going to be. Okay. Okay. So if we assume once again that fluid 1 is the hot fluid and fluid 2 is the cool fluid, right? Okay. Right, so that means T1I. This is the hottest temperature of any fluid that's going to be experienced within the heat exchanger. Okay. And that means T2I. Okay. This is going to be the coldest temperature in the heat exchanger. Okay. So that's not changing. So that's still the kind of the same as before. Okay. Now the only difference here is in counterflow. So if you look at this compared to parallel flow, in parallel flow, the two inlets were right next to each other, right? And so you had that kind of extreme temperature difference at the beginning. Okay. In counterflow, now the two inlets are on opposite sides of the heat exchanger. Okay. So once again, let's make a plot here that kind of plots out the temperatures, and let's kind of talk about kind of what's going on in between those two fluids. Okay. Okay, so let me go ahead and draw our graph here. Okay. All right, so horizontal axis once again is going to be the length of the heat exchanger. Okay. And on the vertical axis here, we're going to have temperature. Okay. So let's once again plot out the our extreme temperatures here. So we know that for fluid one, the inlet is on the left, right? And so we're gonna have T1I, right? That's gonna be the hottest temperature that we're gonna see in this fluid, okay? And then T2I, right? T2I used to be in the bottom left-hand part of this graph because the inlets were on the same side. But now that we've reversed it, now that we're in counterflow, T2I is going to be on the right side of the graph. We have T2I kind of on the bottom right of the graph right there. Right? Okay. Now, what's going to happen between the two fluids is going to be the same. So we expect that the hot fluid is going to cool down, and the cool fluid is going to increase the temperature. It's just that the direction in which they're doing so is different here. Right? So let's do fluid one first. So fluid one, right? Let's say that fluid one decreases from that value at the inlet, and it goes down to T10 at the outlet. So if we kind of connect these with the line. Okay. You can see there that we have, I drew it as if it's linear. It doesn't have to be linear, but linear is kind of the easiest way to draw it. Okay. And then for fluid two, we kind of have to think, opposite, because the fluid two is going from right to left. And so fluid two is going to increase in temperature. And so we can say that, it's going to increase up here. Okay. All right. And then if we draw a line that kind of connects these two, we'll say it kind of looks like that. Okay. All right. And then let me draw arrows here to kind of show you kind of which direction the fluid is going. So we know fluid two is going from right to left. And so you're going to follow the graph kind of like that. Okay. Whereas fluid one goes from left to right. Okay. So let's analyze these graphs here, and let's kind of make note of certain features. Okay. All right. So first thing, let's talk about the temperature difference. Okay. Right. So delta T we know is just the difference in temperature at any given location between fluid one and fluid two. Okay. So, I didn't do the best job drawing this, but, what you should notice is that the temperature difference between the two fluids is roughly constant, is roughly the same at all points in the heat exchanger. Okay. That's a big difference from our parallel flow heat exchanger. So in parallel flow, we had a very high delta T at first, but then it kind of tapered off near the end. Okay. So what this means is that the heat transfer, or the amount of heat that gets transferred between the two fluids, is also roughly constant throughout the entire heat exchanger. Okay. And so that's good. And so, we don't have the same sense of kind of diminishing returns that we had for our parallel flow heat exchanger. Okay. So this has, one very important consequence. And it has a consequence in the fact that, if we were to make this heat exchanger longer, we are still going to be getting good value from it, right? So if we make this longer, we're going to be overall increasing the amount of heat transfer that occurs because that delta T stays constant throughout the entire length of the heat exchanger. Right. So in theory, you can make a counterflow heat exchanger, infinitely long, and then you're going to have well, there are limitations, but you're going to get much more value out of making your counterflow heat exchanger longer than a parallel flow. Okay. Okay. Other thing that you can notice here is that because the fluids are flowing in different directions, right, and because the delta T here is constant, right, it is possible for the two fluids to actually, change in terms of, have one fluid exceed the other one. Okay. Right. So the way to kind of say this is that, it's now possible for the outlet temperature of fluid 1 to be cooler than the outlet temperature of fluid 2.
So there isn't like asymptote like the other one.
Exactly. Yeah. Mm-hmm. Okay. All right, so that's pretty big, and so there are some applications where that is going to be important for those two fluids to kind of exchange in terms of which one's hotter at the outlet compared to the other one. Okay. Now, what are the downsides for a counterflow heat exchanger? Right. Now, I've drawn it in this way just to kind of emphasize this temperature difference, but a lot of times, this temperature difference is not going to be as extreme as the parallel flow. Okay. And so oftentimes, if you are going to run a counterflow heat exchanger, you are going to have to make it pretty long or sufficiently long in order to get the performance, in order to get the effectiveness that you need in order to transfer the total amount of heat. Okay. Okay. So you get better value at longer lengths for a counterflow heat exchanger, but you do need a lot of space in order to do that. Okay. And so, hopefully you guys can start to see kind of the pros and cons of each approach, right? And whether you choose one or the other oftentimes depends on other factors in your engineering design. Because oftentimes the heat exchanger is just kind of one part of your bigger kind of design of a vehicle or your refrigerator or whatever. Okay. And so the general guidelines is that if you only have a short amount of space or small amount of space, so you don't have a lot of room to put a heat exchanger inside your device, then a parallel flow heat exchanger is probably going to be better because it gives you kind of more bang for your buck in that kind of small in that small space. But if you do have a lot of space, if you do have a lot of space to kind of run pipes kind of, past each other for a long period of time, you can coil those pipes up to kind of make a very long length heat exchanger. Then counterflow will give you more value for that longer length. Okay. Any final questions on this before we wrap it up for today?
Not that, like, I'm significant of a question, but if you were to look at the parallel flow heads.
Mhm.
I'm just kind of like looking at the characteristics of it.
Yep.
Would you say that asymptotic line, the red line and the blue line are basically symmetrical and that asymptotic line?
So, I drew it like this just to kind of illustrate it, but oftentimes you're gonna have different fluids between fluid 1 and fluid 2. So you might have air and water or water and oil. So if you have a perfectly symmetric line like this, it probably means you have 2 of the same fluids. You have water and water or oil and oil or something like that. But if the fluids were different, then it would, it would skew more towards one or the other. There would still be an asymptote. It just may not be right in the middle between the two
Okay.
fluids. Yeah, good question. Yeah.
For the counterflow, what are the velocity play like a huge one?
It does impact the heat that gets transferred. So you remember this this formula that we had up here, this one. So the velocity will change the m dot. So the higher velocity that you have, the more heat that can be exchanged between the two fluids. So it does make it more efficient. It does also increase turbulence. That also enhances the heat transfer. We'll get more into that on Thursday when we start computing Nusselt numbers. Yeah. Any other questions on this?
We're not gonna talk about, what was it?
No, unfortunately not. We're gonna focus most on just concentric too. Yeah, no time. We gotta get to radiation, buddy.
How much, more complicated?
It's not that complicated. You're basically combining external flow, like flow over a cylinder, compared with internal flow. It changes this equation a little bit too, because you can't, it's harder to compute Q for the external flow. So you're gonna be mostly based on the internal flow.
Do you have to take into account like the bits essentially?
A little bit, but then it changes your Nusselt correlation. That's the main.
And the Nusselt correlation is.
That's what you use to compute H. So your H values are gonna be different.
It's the, oh, you made us define it in the technically
Yeah.
momentum, diffusivity in terms of thermal.
That's a Frankel. We'll talk about it Thursday. Yes. Yes. This one? Oh. This one?
I missed it.
Yes, yeah. So 2 questions, homework 4, 5, and 6. I'll spend homework 6, probably today. And then yep. And then cheat sheet, same thing, calculator, same thing. So there was one lecture, I think it was the lecture right before the first midterm, we started covering introduction to convection. That's kind of where it starts, and it's gonna go until this Thursday will be the last one.
So I like, on one of the notes, I wrote like the line and like this.
Yeah.
So everything after that.
Everything after.
Okay.
Yeah. All right, thanks everyone. See you on Thursday.
I just wanted to give you a heads up, the marketing is gonna be meeting our senior design team on April 30th.
Okay.
Wednesday, I'm sure we'll be here for that Thursday class, so I just wanna make sure you.
Yeah.
Okay, sounds good, thank you. And then me and Bill.
Yeah. I think there's one.
They're before.
Okay. I think Andrew, you're also informing, right? You're also informing.
Oh, yeah, I was gonna say.
Okay. Yeah, so I need to book a room for you guys. So I'll email you guys, just because
You and Bill? Yeah.
because I think all 3 of you won't fit in my office, so I think I'll probably, actually, you were gonna take the DSS.
Yeah.
Okay, yeah, that's fine. So I think if it's just you and Bill, you can take it in my office.
Okay.
Yeah.
Question.
Yeah.
So I was just wondering, what do you think would be best to do to like prep for the midterm? Like besides the homework?
So I mean, I would definitely look at the study guide
Okay.
for the conceptual questions for sure.
Okay,
And the examples of class, I think people kind of neglect.
okay,
And actually, if you look at the lecture notes, there's actually quite a few examples. I skipped the
Okay.
lecture notes. And so if you go through the lecture notes, you'll see some more
Okay.
examples. So those are useful.
this midterm I'm just a little more worried about because the past few weeks I was locked in on Arrow.
Oh,
I
yeah.
haven't been able to devote as much time as I.
Let's,
Hmm.
study group. Hold on.
Okay.
Let's do it.
Yeah, you guys should study to get, that's, I think that's the best way to kind of study.
All right, thank you.
Yeah.
Okay.